Today we're going to start Chapter 4, the applications of derivatives. We're going to start using derivatives in a functional manner. Yes, we discussed it earlier. Y prime, same thing as f of prime of x, dy dx. But what do they mean? Let's look at this, define what they mean, and I'll show you where we're going to go next. What does all this stuff mean, the derivative? Yeah, there's a difference between 2 points, so it's the slope. Another name for it? Rate of change, very good. And that's pretty much all we discussed so far in those two. Another use of the derivative is called optimization. Finding optimal solutions to problems. We do that by finding extreme values. So the first derivative, yes, we discussed finds the slope rate of change. Now we're going to look at from a point of something called optimization. Also from the first derivative, it helps us draw graphs of polynomial functions. So in this section, in section 4.1, we're going to look at finding the function if you're given the derivative. We're going to work backwards, not in an antiderivative sense, but in an algebraic sense. So that's one of the things we're going to do with it. And then we're going to discuss something called the mean value theorem. And we're going to use that to determine whether solutions exist, and if so, where and how many. Okay, so section 4.1 is called how to locate and identify extreme values. What do you think extreme values mean? When I say extreme values, what do you think I'm talking about? Yeah, actually, that's what we're going to use. We'll discuss that when we do with the mean value theorem. But yes, it does have to do with specific points. The two extreme points are maximum and minimum. Maximum and minimum. From algebra, what do you think maximum and minimum refer to? Highest and lowest points, right? We have highest and lowest points. And there are two types we're going to talk about, local and global. Let's look at the definition first. F of x is a function on a specific domain. And has an absolute maximum value at some point C, which is inside the domain of the interval AB. So the maximum, if f of x is less than or equal to f of c, for every x in the domain AB, then f of c is the absolute max. First, if we're in a domain, let's say A is here and B is here, and C is some point between A and B, because it's contained in A and B. Closed. So the highest point of the graph, this is f of c, it's higher than all the other f of x's in that domain, because f of c is greater than all the f of x's, all other f of x's. Conversely, what would you think the absolute minimum is? If f of x is greater than f of c for every x in the domain AB, then f of c is the absolute So if f of x is greater, all the other x's are greater than f of c, f of c, for every x in the domain, then f of c is the absolute minimum. Here's our f of c. If the value of f of c is lower than all the other values of that function in the domain, and it extends even further than that now. If it's absolute, then we don't have to stay within a bound, a finite bound. It could be an infinite bound, all real numbers. In other words, we can go from negative infinity to positive infinity if it's absolute. The maximum is it's larger and higher than all other functions. The absolute minimum is lower than everything else. Function x squared is a perfect example. Okay. The function f of x squared and f of x negative x squared are perfect examples. What are the domains of both of these? All real numbers. From negative infinity to positive infinity, both of them. The range of these functions. Well, let's just look at the graphs. What does the graph of x squared look like? Parabola, there you go. It's a parabolic curve. Parabolic curve. And negative x squared opens down. So what's the range of the first one? Yeah. Y is greater than or equal to 0.
Why is it greater than?
Because what if x is 0? What's y? Is it in the domain? Is it in the range? If you plug in the values of the domain and it is in the graph, then you have to include it in the range. It starts off at 0 because that's the lowest point. Likewise, this one. This one, the range of the negative is y is less than or equal to 0. Since 0 is the lowest point of this graph, the absolute minimum is f of 0 equals 0. So the absolute minimum is 0 at x equals 0. Because all other f of x's in the domain, which is in all real numbers, will give you a value higher than that. And the negative x squared function has an absolute maximum at absolute maximum of 0 at x equals 0. Because f of 0 is a larger value than everything else I put in there. That make sense? Right. Let's look at two more functions. In the domain negative pi over 2 to pi over 2. Y equals cosine x, and then y equals sine x. Well, no, it's got to be a closed interval right now. So tell me where in both of those you have absolute maximum, absolute minimum. And what values are they? What is the graph of cosine from negative pi over 2 to pi over 2? What's the graph of cosine look like? Right. When x is 0, cosine is 1. At pi over 2, what is cosine? So there's that graph of the cosine function. So, does it have an absolute maximum? What? Equals 1 at x equals what? That's you. Do we have an absolute minimum? Because in our domain we have two of them that have the same value. In order to be absolute, one value has to be greater than every one of them. Since we have two of them, there is no absolute minimum. Y equals sine x. What does that graph look like in the domain negative pi over 2 to pi over 2? What is sine at 0? What is sine at pi over 2? What is sine at negative pi over 2? So the absolute maximum is what? Is 1 at x equals what? Over 2. So the minimum is at x equals negative pi over 2. So this is what we call the maximum minimum values. We call those extrema. Called extrema because that's the plural of extreme. So, the extreme value theorem states this. If the function f of x is continuous on a closed interval AB, then the function f of x gets both an absolute maximum and an absolute minimum in that closed interval, AB. What this says is there are numbers x1 and x2 in the closed interval, the specific domain, where f of x1 equals the minimum, f of x2 give us the maximum, where the minimum is less than f of x is less than the maximum. Every x in the interval. Can they be the same point? And x1 and x2 be the same value? Well, it'd be the only one, but yeah, it has to be a continuous function. When we describe continuity, what does that mean? That there has to be a flow of numbers. It just can't be a single point. So in other words, you have to be able to have x1, x2, where x1 is less than x2. You have to have a sequence of numbers. So no, it has to be a function that is continuous. It cannot be a single point. A single point is not continuous. So what this says, so the function f of x is continuous over a closed interval AB and absolute max and min exist. Why does it have to be in a closed interval? Exactly. Because a perfect example is a sine function. Because it's in a closed interval, negative pi over 2 to pi over 2, the extrema points could be at the endpoints. The extrema points could be at the endpoints or at any intermediary point between there. The extrema can be at the endpoints or any intermediary points in the closed interval AB. So that's discussing absolute extrema. Now we're going to look at local extrema, or what's called relative extrema. What do you think this one talks about? What do you think the difference between local and absolute? Can you have multiple absolute maximums? Absolute is absolute. There can only be one. Local or relative extrema, you can have numerous numbers of them. Let's look at the definition of it. A function f of x has a local maxima u at C within the domain AB. If f of x is less than f of C, for every x in the domain, it is local if domain is a subset of the, that's how I call it, universe. Now for the locals, The local X is in the open interval. The function has a local minimum at C in the domain if f of x is greater than or equal to f of c. Every x in the domain. The domain is some open interval AB. Can absolute maximum minimums be local also? Yes, because it all depends on which domain you look at. Because now the difference between absolute and local is the absolute is the entire picture, is the domain of the entire function. Local are any specifically subdivided. You can have multiple local intervals on a domain. For example, say we had this graph. Let's look at the important points. Let's call this A, B, C, D, E, and F. How many extrema do I have here? Remember, extrema refers to highest and lowest points. Vertices, in other words. How many vertices do I have? How many high and low points do I have? Here's 1, 2, 3, 4, 5, 6. Yeah, because you also have to look at the endpoints also, because if the domain itself is between here and here, we have the absolute minimum of this interval is A, at A, absolute maximum is at B, but it's also local to there. So this is a local max. Why can it not be the absolute max? No, because it's not highest point. Because this point's higher than this point. So this is another local maximum because this point is higher than that. This one's the absolute max. It's the highest of the entire graph. How many local minimums do we have? Is that the very lowest point? No. So it's local. Local min. And this one is the absolute max. What's that?
Is it an absolute min?
No, yes, I'm sorry. Very good, thank you. But these are also local mins and local max. Because the subdomain I can pick would include only those two. So it's a local min, local max. So if I asked you to list the number of local maximum minimums, you would have to include the absolute values as well, the absolute maximums. Also good? So you notice that we're focusing on the vertices and the endpoints. That's going to be a clue for things to come. The extrema. Oh, don't say limits, because we're going to have to do that again. It's the derivatives, yes. What's the value of the derivative at those points? Why 0? Yeah, because the slope of that point at the vertex is a horizontal. Its slope is 0, so the derivative is equal to 0. I'm letting out a lot of stuff out of the bag right now, which will lessen the dramatic effect later on. Okay, so let's look at finding extrema. The theorem. The derivative, or the first derivative, we're dealing with that now. The first derivative of a function any local extrema is this. If the function has a local minimum or maximum, let's do that first. Function has a local maximum value at an interior point in the domain. Function has a local maximum value at an interior point in the domain. And the derivative of that function is defined at C, any point C where C is inside the domain. Then the first derivative at C equals 0. Point C, f of C is the location of the local max. What does interior point mean? Its value at an interior point. in the domain. What does that mean? It has to be, yeah. If your bounds, if your domain is A and B, then the point in which the slope is 0 has to be within that domain. It's interior of that domain. Why is that? It's because we're looking at open intervals right now. We're going to include the endpoints in the next section. Well, in the next sentence, pretty much. Because what we're going to look at, here's a note. F, the function f, and only at extrema at three conditions or locations. Interior points where f prime of x equals 0, interior points where f prime of x is undefined, and the endpoints of the domain of f, of the function. A function f can only have extrema at interior points where the first derivative equals 0, interior points where the function is undefined, we'll talk about that in a second, and then endpoints. What does number 2 mean? What does B mean? Function points where the function is undefined. What is f? What is the process of finding f prime? How do we do it in chapter 1? It has to be a continuous function. The limit of the function has to approach that value from both directions. If it's undefined, what does that mean? That means it's not a continuous function, or the limits don't approach the same value. Now, why can't it have a local maximum or extreme at those points? Because we have a jump discontinuity here, in this subinterval, you have a minimum and a maximum. Well, don't really, because it's an open circle. The point has to exist. This one does not have a local maximum. This one has a local minimum, but no local maximum. On this domain, for this function, it has a local minimum and it has a local maximum. It's not global because it's not a continuous function. Another way it could be undefined. Remember, if you have a point, if your graph has a point, the limit doesn't exist at that point. obviously, the interior points for f prime equals 0, that has to be continuous because the limit has to exist in both directions. The end points, because those are the beginning and the ends of that function, they have to be included because it's a closed interval. The only one that's a problem is this one. But because it creates sub-intervals, we can find local minimums, local maximum. We cannot use absolutes, but we can find locals. Another name for absolute extrema is global, because it's throughout all the entire domain. Points. An interior point on the domain of F where F prime of X equals 0 or is undefined. Actually, this would be F prime of C. Remember what C was in the last definition? Well, C is the value, is the point, is a number in the domain of f of A, f b, that is either greater than all the other points or less than all the other points. What would this one be? Local minimum or local maximum? What would this top one be? That's maximum because it's bigger than everybody else. And this one is min because it's less than. The C has a name. I forgot to give you the name. It's called the critical value. Critical value is the number, the value, the number in the domain that makes the first derivative equal 0. So the critical points are the points that correspond to the critical values. The critical value, I'm sorry, the critical value is the point, is the values inside the domain where the first derivative equals 0. Critical values are the numbers, so the values inside the domain where the first derivative equals 0. The critical points are the corresponding points at the critical values. They're the actual, in short, they're the vertices. They're the locations of the vertex of each of these curves. We call this Theorem 1. Extreme values of a continuous function f of x on a closed interval so could extreme values on a continuous function in a closed interval. What does that mean? I mean, you can only find, the extreme values can only be found if the function is continuous and it's continuous in a closed interval. Extreme values are only at critical points or endpoints. Extreme values are only at critical points or endpoints. Case in point, let's look at the sine function again. From pi over 2 to negative pi over 2. It says extreme values are only at critical points. Is this a critical point? Yeah, because if we continue the graph even further, what's the slope of that curve? Zero. And if we continue this curve, first derivative at that point is 0. The extreme values only exist at the critical points. How do we find absolute extrema of a continuous function on a closed interval? This interval, because it has an A and B, it's bounded, we call it bounded, it's finite, and it's closed. Very important. Why is being closed important? Well, remember, we could only find extreme values at interior points where the first derivative equals 0, interior points where the function is undefined, or the derivative is undefined, or at endpoints. Because it's a closed domain, we have to include the endpoints. So that's why it's finite within A and B. And it's closed. That makes it much easier. So, to find those, the first thing we do is find all critical values. How do you find critical values? Take the first derivative, set it equal to 0, and solve for x. At that point, that is x equals c. That's the point the points, the x values that make the first derivative equal 0, those are our extreme points. These will be maximum or minimas. So let's first find all the critical values. Then evaluate the function f of x at all critical value points and at the endpoints. So evaluate, what does it evaluate the function at mean? Plug them in there. Because if your closed domain is 2 to 7, plug in 7 to the function, see what the values are, and then all the critical values you find. Once you do that, then all you have to do is compare which one's highest, which one's lowest. Then only take largest and smallest points of the function. Find the critical value or values of f of x equals x squared. So how do you find the critical values? Here. I'll put the steps over here. Steps to find critical values. 1. Find the first derivative. So our first derivative is 2x. Set your first derivative equal to 0. So it's 2x equals 0. Solve for x. That's our critical value. Another one. Find the critical values of x6 plus x5. Let's do that easy. Plus 3. Find the critical values. So what's the first derivative? 6x5 plus 5x4. That's it. And that goes to 0. Set that equal to 0. How would you solve it? Common factor, which is what? Take out x to the fourth, gives us 6x plus 5 equals 0. Then set both of those factors equal to 0. Bless you. Once you take the derivative, set it equals 0, solve, and then take each of the factors, set them equal to 0. So x equals 0, and x equals negative 5 over 6. Those are my critical values. Yeah, I was going to say let's go and find out if one of those two would be the absolute minimum. What is this graph going to look like? What does this graph look like? What's the degree of the function? The degree is the highest exponent. So it's degree 6, which tells me one thing, that the end behavior of the graph, both ends point the same direction. Since it's positive, they both point up. We'll have at the most 6 x-intercepts. But the only thing we know for sure, at 0, when x equals 0 equals 3, that is one of our vertices. And then at negative 5/6, we plug that in there, and we would find the second vertice. It would be negative somewhere there. So we could guesstimate the graph's going to look something like this. It may have more curves, but we know for sure that we have only 2 vertices. Well, no, we can't have this over here because there's no other vertex. So since it may just keep on going like this. We can't have that one. We only have 2 vertices. So we can estimate that negative 5/6 would be our critical value of the absolute minimum. Let's look at one using a domain. Given f of x equals x squared on the domain -2, 4. Find the absolute max and min. Another derivative is 2x. No surprise that our critical value is 0. Now what do we do? Once we take the first derivative, set equals 0, find the critical values, how do we find the absolute maximum minimum? Or even local maximum minimum? We take the critical value and the endpoints. This is closed interval. So x equals -2, x equals 0, x equals 4. Plug them back into your original equation. -2 squared is 4. 0 squared is 0. 4 squared is 16. We pick our maximum minimum for these guys. So the smallest number is 0, so this is my absolute min. The largest is 16, so that's my absolute max. It just so happens at the endpoints. For the function 10x 1 or 2 minus ln x. On the domain 1 e squared. Find the max min. Absolute max min. The derivative will be the hardest part. F is 10x, g is 2 minus ln x. The derivative of 10x is 10. The derivative of 2 minus ln x, negative 1 over x. So we have to do the fishy thingy. 10 times 2 minus ln x plus nx times negative 1 over x. Minus 10 ln x minus 10 minus 10 ln x equals 10 times 1 minus ln x. Good. How do I do? Take this equation, set it equal to 0. First step, divide both sides by 10. 1 minus ln x equals 0. Ln x how do you solve this one? Well, we know that ln x is log base e of x. E to the first power equals x. So x is equal to e. The conversion of a logarithmic equation to an exponential equation. Don't remember it. Log base a of b equals c. A remains the base. It just comes over here as the base of the c. So that's the conversion rule. So what is e? What does this represent? Critical value. So the 3 points we have to test for extrema, x is equal to e, x is equal to 1, and x is equal to x squared. X is equal to e, x is equal to 1, and x is equal to e squared. We plug those back into the original function. And x 2 minus ln x. Once we do that, then we pick the highest and lowest numbers, and those are our extrema. So f of e. And e 2 minus ln e. And e. What is ln e? 1. Next one. F of 1. n 1, 2 minus ln 1. What is ln 1? Log base anything of x equals 1. That's that one. But now, log base a of 1 is equal to x. The only way that's true is if x is equal to 0. So ln 1 is 0. And then for e squared. 10e squared, 2 minus ln e squared. The exponent comes down in front. Ln e is 1. 2 minus 2 is 0. So do we have a obvious winner? What's the maximum? What is the value of e? It's 2.7 something. So 2.7 times 10 is 27. It's bigger than 20, so this is our max. This is our min. Right? Did y'all receive that cheat sheet I sent y'all? I want to hope it's helpful. If not, I'll get this class a bigger one that has everything, even for calculus 1, 2, and 3 in there. There's another example. F of x equals x to the power 2/3 on the closed interval 2 through negative 2, 3. Find the absolute max and min. So the first thing we have to do is find the first derivative, which is 2/3 x, subtract 1 from the power. So we have 2 over 3 cube root of x. That's the first derivative. Two over 3 cube root of x equals 0. What's your conclusion here? What do you remember from rational functions? Well, we can have x on the bottom, but well, we can, but we're not supposed to. If we have x on the bottom, that's going to be a asymptote. But this is looking for the slope. The only way a rational expression can be equal to 0 is if the top is 0. Can the numerator ever be 0 in this example? No. So, no critical value. And the critical values, we have to take x equals -2 and x equals 3, the endpoint, and plug it into our original equation. F of -2 is -2 to the power 2/3, which is equal to cube root of -2 squared, which is cube root of 4. And f of 3, 3 to the power 2/3, which makes it cube root of 3 squared, which is the cube root of 9. So my question is, which one's bigger? This is max or min? Max or min? $50-50 shot to sound intelligent. Or the opposite. Is what? Cube root of what? Yes. That's the max. Right. Cube root of anything, you just go, so it's the same root on both of them. Just look at the numbers. 9 is bigger than 4, so that one's got to be bigger. Good job. That's the end of that section. We're going to start using a lot of this stuff as we go on, because when we start graphing equations, you're going to have to remember what you did in algebra. Remember Descartes' rule of signs, the whole synthetic division process of finding the solutions to higher order polynomials? We'll have to review that. Because what can you find from the original function? When it comes to graphing and looking at functions of operations, what does the original function tell us? Tells us the shape, because the degree of the equation tells us the shape, whether the end behavior is up or opposite, which one's, if it's a positive or negative function. What else does it tell us? It also tells us the x-intercepts. We know what the graphs look like, whether it both we know where the x-intercepts. And then what does the first derivative tell us? Yes, actually the slopes would be important. But what did we just find today? What were we looking for today? What? The extrema. The extrema, the absolute or local maxima or minima, which are the vertices. Now, if you look at a vertex, its slope is 0. That means numbers to either side of those have to have different values, different sign values. If you have a vertex that's a maximum, on one side it has to be increasing, the other side it has to be decreasing. So one side the first derivative is positive, one side the first derivative is negative. And at the vertex is 0. So you can tell whether it's a maximum or minima just by looking at the values on both sides. If it's a minima, on the left-hand side, the slope's going down, so it's a negative slope. On the right-hand side of a minimum, it's going up. That's what we're getting to in the rest of this chapter. Oh, nope.